Have you ever wondered how a video game character knows exactly where to jump? Or how an air traffic controller can guide a plane they can't even see? Well, it's not magic, it's math. And specifically, it's about two really powerful tools that let us describe the world around us. So today, we're going to take a journey from simple, static arrows all the way to the elegant, dynamic arcs they can create. We're diving into vectors and parametric equations. So here's our game plan. First up, we're going to get our feet wet with the basics. What a vector actually is. Then we'll build out our toolkit with some key vector operations. After that, we'll unlock a kind of secret weapon, the dot product, which tells us a lot about the geometry between vectors. From there, we'll add time into the mix to get our vectors moving, and finally, we'll put it all together to see if a football player can make a game-winning kick. All right, let's dive into section 1. What exactly is a vector? Now, it might sound complicated, but trust me, everything we're about to do starts with one really simple, powerful idea, and it's so much more than just a number. I mean, think about it. If I told you to walk 5 miles, what's the first thing you'd ask? 5 miles where, right? Without a direction, that number is almost useless. You're missing like half the story. And that is the exact problem vectors were created to solve. And here it is, the solution, a vector. You see, it's not just a plain old number, which, by the way, in this context we call a scalar. A vector is a package deal. It always contains two crucial pieces of information. Its magnitude, which is just a fancy word for how much, and its direction, or which way. Visually, it's super simple. A vector is just an arrow. The length of the arrow tells you its magnitude, and the way it's pointing, well, that's its direction. But how do we write that down? That's where these angle brackets come in. The components, like 3, -1, 1, are basically a set of instructions. Go 3 units along the x-axis, -1 on the y-axis, and 1 on the z-axis. And you've got to notice those angle brackets. That's key. It signals a journey, a kind of displacement, which is totally different from parentheses that just mark a fixed point in space. Okay, so now we know what vectors are, but let's get to the fun part and see what they can actually do. In this next section, we're going to build our vector toolkit. These are the essential operations you need to really put these arrows to work. You know, what's really cool is that working with vectors visually is just so intuitive. If you multiply a vector by a regular number, a scalar, you're just stretching it or shrinking it. So multiply a vector by 3, you get a new vector that points the exact same way, but is 3 times as long. And adding 2 vectors, say A and B, is like taking a trip with a layover. You follow vector A, then from where you end up, you follow vector B. The result, vector C, is the direct path, the shortcut from your starting point to your final destination. And here's the amazing part. That simple visual logic translates into incredibly simple algebra. Just look at this table. To add 2 vectors, you don't need to draw a single thing. You just add the first components together, then add the second components, then the third. Same deal for subtraction. It's clean, it's elegant, and it just works. But what about finding the actual length of one of these arrows? I know this formula might look a little intimidating, but it's really just the Pythagorean theorem in disguise. You just square each component, add them all up, and take the square root. That's it. You've just found the magnitude. So we can add and scale vectors, but what happens if we want to multiply them? This is where things get really interesting. Our next tool, the dot product, is a special kind of multiplication that doesn't just give you another vector, it actually unlocks the geometric secrets hidden between 2 of them. And calculating it is surprisingly easy. You just multiply the matching components of the 2 vectors, so the x's with the x's, the y's with the y's, and then you just add all those little products together. Okay, you're going to want to lean in for this part, because this is the #1 thing people get mixed up. When you dot 2 vectors together, the result is not another vector. It's a single number, a scalar. You're taking 2 complex objects and boiling their relationship down into one single meaningful value. So why is that one little number so important? It's because of this beautiful formula right here. This is the bridge between the world of algebra and the world of geometry. It shows us that the number we get from the dot product is directly connected to the actual angle between the 2 vectors. This means we can find the exact angle between any 2 arrows in space just by doing some simple multiplication and division. No protractor needed. And this leads to a super elegant trick. Think about it. If the dot product of 2 vectors is 0, what does that mean? Well, it means the cosine of the angle between them is 0, which only happens when the angle is exactly 90 degrees. So if the dot product is 0, you know instantly, without a doubt, that those 2 vectors are perfectly perpendicular or orthogonal. It's a really powerful algebraic shortcut to test a purely geometric idea. Okay, so we've been playing around with these static arrows, but the real world isn't static, right? Things move. So in this next section, vectors in motion, we're going to breathe some life into our vectors and make them dynamic. And that brings us to a really important question. A vector can tell you where to go, but it doesn't tell you anything about the journey itself. It doesn't tell you how long it takes or where you are at the halfway point. To capture all of that, we need to add a new ingredient, time. And we'll usually represent it with a parameter, t. And this is exactly what parametric equations are for. You know, on a standard graph, y depends on x. It just gives you a static picture. But with parametric equations, both x and y depend on a third variable, t. It's kind of like having a director for your graph, telling your point exactly where it needs to be at every single moment in time. So how do we actually visualize what this path looks like? Well, the best way to think about it is like you're making a little flip book. You start by making a table. At time t equals 0, where's our point? What about at t equals 1 or t equals 2? You just calculate the xy coordinates for each of those moments, plot those points, and then connect the dots. The final arrow you add just shows the direction of the story, the flow of time. All right, we've done it. We've got our complete toolkit. We understand vectors, we know how to do math with them, and we can use parametric equations to describe how they move through time. So for our final section, let's put it all together and tackle a classic real-world problem. And I want to be clear, this isn't just about problems in a math textbook. This is literally the language of reality. From the path of a football to the orbit of a satellite, from the physics engine in a video game to the flight path of an airplane, vectors and parametric equations are the engine running silently in the background. So let's take this classic physics problem. We've got Spencer, and he's kicking a field goal. We know the goalpost is 40 yards away. That's 120 feet. The crossbar he has to get the ball over is 10 feet high, and we know his kick launches the ball at 65 feet per second at a 45-degree angle. So the million-dollar question is the kick good? Will he make it? Now, the only way to solve this is to treat the horizontal and vertical motions separately. We use a little bit of basic trigonometry to break that initial 65 feet per second velocity vector into two pieces, how fast the ball is moving forward and how fast it's moving upward. This gives us our two parametric equations. The horizontal one is pretty simple, distance equals rate times time. But the vertical one, that one's more interesting. It has the initial upward motion, but it's constantly fighting against the downward pull of gravity, and that's what that negative 16t squared term you see here represents. Okay, so first, we use the horizontal equation to figure out when the ball gets to the goalpost. A little bit of math tells us it takes 2.61 seconds to travel those 120 feet. Now, for the moment of truth. We take that exact time and we plug it into our vertical equation to find out the ball's height at that very moment. And the answer is 10.967 feet. The crossbar is 10 feet high. He clears it by less than a foot. The kick is good. So there you have it. We've gone from simple little arrows all the way to the arc of a game-winning kick. We've seen that vectors give us the language to describe things like force and direction, and parametric equations give that language a timeline. So the next time you see a plane flying overhead or watch a ball fly through the air, I want you to try and see the invisible vectors that are guiding its path. And then ask yourself, what else in my world is defined by both a magnitude and a direction?